All right, I think we'll get started. First of all, thank you very much for all of you coming today. Very excited about the talks we've got coming up. Just a bit of housekeeping first. We'll be recording this and we'll be putting it on our YouTube probably in the next week or so. If everyone could turn off all their microphones and their cameras so we can just focus in on the speakers. We've got 3 speakers today. We're going to have questions after each session. But if you could write your questions you have in the chat and maybe make it clear who you're asking as well, just so we know who to direct to. I've got also Sam Young, our data science and AI lead at the Catapult, who will be helping in the chat as well and sharing some materials. Please. Thanks very much for all coming. Let me do a quick introduction. I'm Stephen Haven, I'm a data science consultant at the Energy Systems Catapult. This is a webinar on AI for unlocking domestic decarbonisation. It's part of the advice programme. Bill will talk a little bit about what that is. It's a DESNZ funded project, and we've got a few other materials on that we'll share throughout. As I said, we've got 3 speakers. I'm very excited about this. We will start with first our own Bill Jenkinson, who will be talking about sort of the context and opportunities in decarbonising residential heating. Then we've got 2 speakers from different organisations who will be talking about how they're actually applying sort of AI in some of their solutions. The first will be then Simon Roberts from Heatio, and then Lawrence Oakes-Ash from City Science. Everyone just turn off their cameras and mics, please. So I'm going to introduce Bill. And so Bill, if you want to start maybe sharing your slides while I introduce you. Bill, he's our internal advisor on building decarbonisation here and at ESC. He has a wealth of experience in this area and knows all things retrofit. And he advises and leads decision makers in the fields of domestic low carbon solutions from conception to product development. So I'll leave it to you, Bill. Go ahead. I can see your Windows slide. Yeah, there you are. Yeah, that's the
one. Good morning, everybody, and thanks very much for listening to me today, but also thanks very much, Stephen, for the opportunity to talk today. So today we're here to talk about the advice programme, and the focus of my talk today is around domestic decarbonisation. First of all, we want to just talk about the Energy Systems Catapult. So our overall mission is about unleashing innovation and opening new markets to capture the clean growth in net zero opportunity. We're based in Birmingham. We're more than 250 people now. We're independent and not for profit, and we were established by Innovate UK. We have a wide range of support services that we offer SMEs, but we also offer customer insight, proposition design, whole system modelling. We're experts in data and digital. We do markets and regulation. We deliver trials and demonstration projects and research projects for DESNZ, for Innovate UK, and for commercial organisations as well. We take a whole systems approach to this, so we look at the full energy system and all the stakeholders that are playing part in that in this net zero journey. Advice, so AI for the decarbonisation challenge. So this is around looking at Stream 1, which is a DESNZ AI programme. The aim is to engage AI and decarbonisation stakeholders. So we're looking for cross-sector collaboration and coordination, define key decarbonisation challenges that are that AI might be able to play a solution in, and obviously disseminate the information to the relevant stakeholders. The sector focus are energy, built environment, manufacturing, and agriculture. three categories of AI application, which is the sum around industry, which is obvious applications of AI, very little decarbonisation impact in some of those. Applications of AI targeted and obvious direct decarbonisation impact, and then applications of AI targeted at less obvious systematic blockers to decarbonisation. For this particular view, we're looking at particularly the one that's highlighted in number 1, which is unlocking domestic decarbonisation. There is other calls and other challenges which are highlighted here that you can read at your own leisure. So the big headlines here. 80% of UK homes are heated by natural gas currently. 80% of home carbon emissions are heating. This excludes lifestyle choices, which are around maybe flights, travel, maybe diet. But what we're saying is that 8% of the actual home's emissions are heating. Gas boilers generally have a 15-year life expectancy, but we are racing towards 2050. And we know by 2050 we need to have reduced carbon emissions from heating by 95%. We recognise that there's no silver bullet, but we also recognise that heat pumps and district heatings are the leading low carbon solutions for home decarbonisations currently. So first topic that we're going to get into today is heat pumps. And what we're looking at here is what we need to do and how heat pumps and the thorny issues with heat pumps. So we need to move from left to right. So we need to move from gas boilers to electrically powered heat pumps. So we need to move from fossil fuel boilers solutions that to solutions that can harness renewable energy sources. But there needs to be large design considerations, and installers need to consider more about how radiators work at lower temperatures, but also reducing the heat loss of the building overall by improvements to the building fabric. This all creates data, and this all creates data that needs crunching to actually be able to do careful design around the new heating solution, so it can be effective and efficient. So this is an example of how a gas boiler works and how a heat pump works in terms of what the kilowatt input would be, what you get out of the boiler, and what the typical cost per hour would be for a gas boiler compared with a heat pump. Now, worryingly, you'd say at this point, wait a minute, Bill, it's always going to be more expensive to run a heat pump than a gas boiler. But we are using this SCOP of 3 just because it's simple, because it gives you a simple idea of how a heat pump actually works. So we take 1 kilowatt of electricity, we have 2 kilowatts of renewable energy coming in, and we get 3 kilowatts of heat out. Now, this gives you an overall idea of how it works, but we can do lots of things to actually determine how we're going to improve this heat pump value back to the end customer. So if we look at the SCOP, we can improve the SCOP, which is the seasonal coefficient of performance, or we can adjust the price that we're paying for electricity currently, so the spark gap compared with gas. The other thing that this demonstrates quite clearly is the high carbon impact of gas boilers compared with something like a heat pump. So why is designing a heat pump important? Most UK homes at the moment, as we've said, use combi boilers. These are instantaneous hot water devices. So once you turn your tap on, the boiler fires. It instantly heats cold water to hot by using high intense energy sources. Generally, these boilers are oversized for space heating, and the installers have never really had to consider the design of the heating system in relation to the size of the boiler. Gas boilers generally are one size fits all, but this is not the case for heat pumps. If heat pumps are undersized, they will not provide enough heat, resulting in high heating costs and ineffective heating. So I think we see this, this has been in reports quite often, that heat pumps don't work. They do work, they just have been designed badly or specified badly for the scenario that they've been put into. Oversized heat pumps can also be problematic. What tends to happen, if you understand how a heat pump works, it means that you won't get the full benefit of the heat pump because a lot of the power is used with the compressor starting up, and you don't get the full advantage of the renewable heat that's there to be harvested as part of this. So if you get large cycling, it leads to poorer performance and higher heating costs. We've tried to map this in terms of systematic blockers to the rapid heat pump adoption, which are around design challenges, which leads to complex time and consuming installations. This leads to negative perception, but also high upfront costs. There's a skills gap that's been recognised here, as we spoke about. The sizing of heat pumps is difficult, which leads to also a negative perception, because if you don't know how to size a heat pump, then you're not going to recommend one to an end customer. There's a variable installation quality, which can lead to higher running costs, which again leads to a negative perception of heat pumps. So what can we do about it? I thought it'd be useful at this stage to actually show the as-is journey. So generally, if you're a customer and you ask an installer for a heating solution for your home, they're going to recommend a gas boiler. If you are really interested in a heat pump and you go to an installer and ask about a heat pump, you're probably going to get recommended generally a gas boiler. If you're lucky enough to find a heat pump installer, then actually what ends up happening is that you end up with quite a long process compared with a gas boiler, the as-is now journey, because you've got some design challenges. You've got complex time of installation. We know that we'll get a variable quality of installation at times, and we know that there are higher upfront cost and a higher running cost. If we look at this, you can see, again, we're producing lots of data within this journey, and we've got different options that we can choose in terms of heat pumps. The AI challenges and the categories have been categorized quite clearly here, which is around design and planning, maintenance and anomaly detection, management and operations, and incentives and customer support. What does this really mean for a heat pump, and how AI could be used to actually size a heat pump more correctly and actually bring in bigger data sets? So we know at the moment there's lots of data out there about existing housing stocks. This will grow in the future, and we will get better at feeding the AI solution, which can better predict what these houses. So I think you got the bits about housing stock and the fabric, and how the fabric and the radiator sizing can be fed into this AI system. And then the heat pump characteristics can also be fed in, which leads to a direct AI customer relationship, which then can inform the installer about the right heat pump for the right home. This will eventually lead to lower installation costs, less human error in design, an OEM, so a manufacturer agnostic heat pump best fit. It'll lead to improved heat pump performance and leaves installers to focus on what they actually want to do, which is install. Maintenance and management. So when we think about what AI could do from an overall control perspective for a heat pump, so we can learn about the home environment as it's running the heat pump. It can adjust automatically and get the heat pump to adjust and to really think about how that home heats up, about how the home will retain heat, about how the customer wants to, about the customer's comfort needs and how it can meet them comfort needs more effectively. It can also take signals from the electricity system, to actually bring in better costs in terms of electricity, but also take advantage of flexibility options. It can look at weather forecast data and consider preloading the heat into the building. But it can also help with predictive maintenance and breakdown alerts. This will lead to lower running costs, improved comfort levels, predictive maintenance, improved heat pump performance, and the heat pump owner can take advantage of flexibility without having to do a lot of work. The next category that we wanted to highlight was district heating. So what is district heating? District heating networks are macro solutions for cities, towns, and high density urban environments. The network will contain an energy centre that captures, generates, stores large amounts of heat. These centres can utilise low carbon energy generation and waste heat from industrial processes. Large insulated pipes distribute heat across the network. And each home will have a heat interface unit that will provide hydraulic separation from the network and central heating and domestic hot water provision. It will also contain a heat meter for billing purposes. District heating networks require large capital investment to be built and a certainty of heat supply over a long-term perspective. There's key stakeholders involved in district heating. So the network operator. So the network operator runs the whole network. The investor stakes the money up front and brings it back and wants a rate of return for actually investing in this infrastructure project. There's also the customer who sits and actually is locked into a heat agreement. And actually they've not got much choice in terms of being able to switch away from these heat networks. So it's really the network operator's duty to actually balance the return of investment from the investor point of view and to be fair to the end user. Common problems on heat networks. So district heat networks, effective and efficient operation depend on the build out of the whole system. So what I mean by that is you've got to have certainty of this supply of heat. Otherwise, you might have oversized or undersized the whole of the network. The energy centre is often designed with multiple sources of heat feeding into large heat stores. The efficiency of the operating plan is impacted by the design temperature of the network. The heat loss from pipes can lead to inefficient operation of the network. Just because if you've got higher temperatures, then you're going to get worse heat loss. HIUs are based on providing instantaneous hot water and space heating. To generate instantaneous hot water effectively, It requires large amounts of heat from the network. HRUs are not always commissioned well, which will waste energy. So when we look at this in a macro sense, marginal gains can make a big impact here. So district heat networks and implementation should ensure that all key stakeholders are committed to the build-out. The energy centre will run more efficiently at lower temperatures, and the ability to not pump when heat's not required or to ramp the pumps down and balancing the heat across the network is crucial to an efficient operation. Heat loss from pipes can be minimised through better insulation and installation, but also from lower network design temperatures. HRUs require careful individual commissioning to ensure they do not waste heat when it's not required. HRUs containing hot water storage will enable lower network design temperatures. So the AI challenge categories, again, we're just re-emphasising design and planning, maintenance and anomaly detection, management and operation, and incentives and consumer support. So how can AI help here? So AI can play an important role in the planning and design of future networks to ensure that they have certainty of efficiency of the whole network. It could be used to run complex models that offer operations and provide fair options and fair outcomes for customers, and enables the operator to guarantee with confidence the offer of a high IRR for investors. Optimization of the whole network, commercial optimization, a fair deal for customers, and the ability to provide a transparent way of explaining to customers and who have little choice but to switch suppliers. AI could be also used to better manage heat networks and model maintenance and breakdowns. This will grow in predictability using an automatic feedback loop. We have some challenge cards, and these can be found by actually scanning this QR code. And we've highlighted these where these really start highlighting the challenges that are ahead of us so far. And thank you very much for your time today. I hope that's been useful, insightful. Sorry about the internet drop off, but it's the joy of Teams. But thank you very much, and I'll be happy to take any questions.
Yeah, thanks very much, Bill. Yeah, we've got time for a little bit of questions. There's a lot of questions, actually, so I think we'll have to answer in the chat a lot of them. And my colleague Sam is busy in a way, so hopefully I won't repeat any. But just a comment quote first. Lawrence mentions coordinating smart heat pumps will be another possible AI application. Absolutely, at the grid level, the potential to reduce the grid reinforcement costs. That's true. I think that's a great comment. Wasim asks, what are the typical challenges for designing a heat pump? I guess this one's for you, Bill, rather than talking about specific AI aspects.
So specific challenges, yeah, it's quite interesting. When you design a heat pump, you've got to do a full heat loss calculation room by room for a home. So you have to go in, you have to measure all the rooms individually, but you also have to take the U values for each of the fabric losses for that room. So a U value would be typically the heat loss for that particular fabric. So you'd be looking at your brick walls, if they've got a cavity, if it's been filled the cavity, you'd be looking at the windows, the doors, the floors, the ceilings, and you've got to do this for the whole house. So you can imagine it's not just a case of going in and sticking your finger in the air and going, well, it's going to be roughly about, a kilowatt, 2 kilowatts per hour for this room. Actually, you need to do a detailed design. You also need to consider the radiator size for that individual room to ensure that the radiator can meet the heat loss of that room in the cold weather conditions. So it's quite a delicate operation that you need to consider how to size that heat pump correctly. Heat pumps also need to be sited correctly outside, so that all that needs to come in, because they generally, with air source heat pumps anyway, there's certainly a noise element. So all this is considered in the design. So it is a thorny issue, and we really see this being an opportunity for AI to step up and help installers.
Thank you. I'll just address, Tim asked about the automation. This is maybe more automation rather than AI. I guess it's more about, using the AI to anticipate and plan a bit better than, reacting. So some of it, essentially is trying to replace the reactive sort of automation of some elements. But also we'll have some talks, obviously coming up, which will talk a bit more about the AI itself. Nigel's got a comment here, which maybe I'll address later about the AI aspect, but I guess there's the wider comment. Asks about will the AI algorithm consider the parasitic costs of defrosting in humid environments? In I guess Northern Ireland, we have a humid maritime climate, and the amount of defrosting of heat pumps seems quite high. So maybe that problem in general, you could talk about, Bill.
Yeah, I mean, you're right to mention humid environments, and I think we see that. I think some of it's not just the humid environment though, to be honest with you. It's also running the heat pumps hard, right? I think running the heat pumps hard, and I think what we'll get eventually here, and how AI might step up and do it, is to avoid some of these mistakes that may have been made in slightly undersizing the heat pump, if that makes sense. So I'd suggest they've not been sized correctly for the environment when they've thought about the full humidity. And you could do something about it if you actually sized it a little bit bigger. So that's what we're saying, actually. It's more about taking the full overview of how you're going to size a heat pump and ensure that you're taking this into consideration when you're actually getting the design correct. And I think this leads you actually to the answer that actually AI's probably got a really good chance of doing a better job than a human, if that makes sense.
Brilliant. Thanks, Bill. I think we're going to have to move on to our next speaker, but thanks a lot, Bill. And please, go in the chat and answer some of the questions if you can. We're going to move on to our next one. So, so our next speaker is Simon Roberts, CEO of Heatio. They combine in-home data plus advanced AI to provide insights and bespoke energy efficiency recommendations. And they're currently working with ourselves and E.ON as part of a government's Green Home Finance Accelerator to measure the impact of retrofit measures and develop new innovative funding models. So thank you, Simon. Yes, please share your slides and take it away.
Cheers, guys. Thank you very much, Bill. I'm just going to do my screen share and bear with me.
Yeah, that's it.
There we go. Well, excellent stuff. Okay, ladies and gentlemen, I want to start off by imagining a world where every home not only shelters its inhabitants, but actively works to create a sustainable future. And today, I think we stand on the brink of a technology revolution where artificial intelligence and machine learning kind of converge every day, living, transforming our homes into intelligent hubs that optimize energy use and ultimately reduce costs, and probably most importantly, drastically cut our environmental impact. And I think a crucial part when we talk about kind of AI and machine learning is that this isn't necessarily just the future. This is the reality. We're actually creating these smart connected homes right now. So my name's Simon Roberts. I'm the CEO and founder for Heatio. And fundamentally, we're on a mission to make clean energy affordable to everyone. And we do this by developing technologies and funding solutions that enable the transition to renewable sources of energy. This includes design tools which enable the use of energy data to simulate the impact of energy efficiency improvements in your homes. We also develop home energy management systems to optimize energy usage. And we enable you to earn from those energy assets in your home through energy trading markets, with the aim of converting consumers into prosumers. So we're using data to tackle fuel poverty. We're using data to tackle climate change, And today I'm here to talk to you about the kind of how we're using those advanced technologies like AI and machine learning and how they're shaping the future of home energy. But I think for most, when we think about AI and machine learning, we probably get a view like this. I think maybe not from a technical perspective, but to ask consumers, it's all about robots taking over the world and humans becoming slaves and us being told what to do by the machines we've created. But actually, there's a really kind of simple view to AI, and it's something that we all have been through as children, and that we teach our kids every day, and it's simulated learning, and that's really where we've started to focus our modeling and our data on. And this is just a really simple example of how supported learning and simulated learning can be used in the form of AI. So when we start with this model, the machine doesn't know what an apple or an orange is. So we start feeding images of apples and oranges, and we call these labeled data sets, and we feed them into the model, and the model starts to learn what an apple looks like or what an orange looks like. So then it can start to train itself, and we maybe start to feed in different variations of what apples look like and what oranges look like. And weirdly enough, when I was pulling this presentation together, I had an incident with my 6-year-old when I gave him, he typically eats your kind of Granny Smith apple. So he knows what an apple looks like. He knows that it's green, it's shiny, it has a little stalk on it. And then one day last week, he was given a pink lady. Now, in his head, that wasn't an apple, because his machine, his brain, hadn't been taught that an apple could be anything different than green. So in this scenario here, when you feed in the variations to an apple or an orange, the machine starts to learn and be able to process that information differently, and it starts to be able to segment that data. So if you then came across a situation where you had a huge amount of data or labeled data, various different fruits, thousands and thousands and thousands of images, and you needed a machine to be able to sift through that data really quickly and tell you which of those data sets that you're feeding in are apples and oranges. As the machine starts to learn and you get those varying differences in different types of fruits, the machine starts to be able to predict which are the apples and which are the oranges. Now, in everyday living, we don't necessarily need that too much, but when we start to think about that in the concept of AI, what we're actually asking for is input. We need data input in order to be able to make informed decisions. And I think crucially, when we start looking at that in the form of energy management in people's homes, and some of the points that Bill covered there in the presentation, currently we don't use data to make a lot of the decisions that we make. And I think probably the most obvious one that we come across is when we're designing heat pump systems. Bill mentioned there the process that you go through to design a heat pump system, and that is a very detailed room by room heat loss calculation. And as a heat pump engineer for over 20 years, I've done plenty of those calculations, and the theory behind it is correct. When you have a boiler, you can, within reason, do a relatively finger in the air calculation to determine what the heat loss of that home is. Maybe you look at the existing boiler that's there, and you'll replace it like for like in terms of the output that's required. If the customer's not having any issues with the boiler in terms of meeting the home's heat demands, then you can pretty much replace it like for like. When you start getting into a heat pump, we don't have that same opportunity. We have to design these systems very specific to the home. And the route that we go down is we send a energy assessor in who will measure each room individually and any of the building elements, so any windows and external doors, and we'll make then assumptions around certain factors. We will assume what the makeup is of the insulation, for instance, within a wall. Now, we may be able to use building control data to understand what that should have been at that time. But for all we know, that on that particular home, on that particular day, the builder was having an off day and didn't put the right level of insulation in, or maybe they've had cavity wall and it hasn't been done correctly. So even these very detailed calculations, which take a huge amount of time and add to the cost of having a heat pump installation installed. Fundamentally, when we get down to it, it's somebody with a clipboard or a piece of software inputting data on their best guess assumptions. And that can go very wrong. We can end up with systems that are oversized, which can result in short cycling of the heat pump, which can result in increased running costs. We can end up with them being undersized, which can end up with the customer not meeting the temperatures that they wanted in their home, and again, increased running costs. So fundamentally, we need to start transitioning towards a data-led approach. And one of the programs that we're working on with Energy Systems Catapult at the moment, funded through Innovate UK, is this ability to use data to be able to simulate or predict what size heat pump is needed in the home. And this falls under our category of digital twin. So what we're looking at here, going back to the kind of apples and oranges scenarios, we're labeling this data that we're looking at from the home. So we're collecting the energy consumption data, that half-hourly energy usage across both gas and electric. We'll be monitoring internal air temperatures and external air temperatures, the humidity in the property, and also looking to get LiDAR room scanning technology. So we start to build a digital twin of the property that we can then monitor through various different external and internal conditions. What that gives us the ability to do is calculate something called the heat transfer coefficient. Specifically, if we go for a winter period where we have a period of time where the internal air temperature and the external air temperature are around 7 degrees difference. If we can calculate that HTC in those very specific moments, we can actually start to look at what the actual size of the heat pump is. But more importantly, we start to get to this ability where we can start to simulate the impact of a heat pump on that home, specifically based on how that user, that homeowner, uses their home. So we had a client that came to us that was interested in having a heat pump. We went out, we did the heat loss calculations for that property. We then did what we're required to do under MCS, which was take the space and water heating data from the EPC and use that to calculate how much that homeowner would spend on their heating. And the reality was, in that particular client's case, they very rarely had the heating on. So the actual kilowatt hours on their EPC for space and water heating was very different from the actual. So with these simulation tools that we build, we're able to simulate the impact of a heat pump on that home based on how that person utilizes the energy in their home, how their occupancy is, how they heat their home, how they use hot water. And I think as well, as Bill touched on earlier, you then start to look at what the seasonal coefficient of performance might be for that heat pump. And actually, when you run those calculations for somebody who very rarely has the heating on or has it at lower temperatures, it might be that a heat pump in isolation is not actually the best choice for that particular customer. But then when you start applying things like energy storage into that equation, and you start simulating the impact of adding solar into that equation, all of these things, understandably, increase the capital cost of the installation, but they also have a dramatic impact on the performance of that system. And although at the moment, a lot of this information is speculative, although based on existing performance data, the more data that we start to feed into this model, the more we can start to simulate various different house types. So we start creating, using data to create multiple housing models, multiple occupancy profiles, and they're constantly being fed into the data set to enable more accurate predictions on performance. And that's a crucial step for us, is we need to be able to give visibility to our clients on how their home is performing currently and what it could look like once you start to add these technologies in, so they can start to make informed decisions based on how they use the property, and also being able to simulate things like how their comfort levels might improve. it's absolutely fundamental to be able to move from a data-driven model into an AI and machine learning-driven model by having real-time data feeding into the data sets that sit behind the system. And we know we need to encourage more homeowners to actively engage in the journey right at the start, so we can start pooling their data and seeing how their homes perform, with a view that for those that do then move on and have the technology installed, we then start to monitor this technology and see how it's actually performing in those circumstances. And this is how the model starts to become trained. We've fed the data in, we've made some assumptions, and then the model starts to get trained based on how those systems are actually performing in those homes, in those individual models. And we start feeding that back into the system. So that goes right back to the start. That goes right back into our predictions. If we predicted the home was going to perform a particular way, we've now got the data to determine whether or not our predictions were correct. And that will reinforce any future predictions moving forward. And that goes right the way across the technology stack, but it also looks at things like the climate data and solar radiance based on particular orientations of homes and orientations of panels. So we've got to look at ways in which we can use machine learning techniques, both in that initial prediction of how the home's going to perform and taking the data to constantly train the model and feed back in. But we can also then start to look at ways we can use that data to manage the energy usage in that home. So if we look at a way, if we predict a way that that home's going to perform over the next, say, 24 hours, when we start to take into consideration things like agile energy tariffs, and we tell that system and we send those commands down to the technology and tell it how to perform over the next 24 hours, we can then monitor whether or not we achieved the objective, whether or not we achieved the comfort level, whether or not we maybe overshot the comfort level, maybe we were under the comfort level. So the system starts to learn organically on a house by house basis how to perform. And that's really the exciting parts around this, is that when you start adding in things like EV chargers into the mix, if we start to collect data on people's usage, so for instance, if somebody typically travels to work on a Tuesday and we can see that they, and the rest of the time they work from home, the logic would suggest at the moment that they may plug their car charger in on a Monday night, and that will then look for the cheapest energy period, and it will charge that car up on the at some point in that evening to take it to a full charge. Whereas using data and AI, we may be able to look at ways in which that forecasted weather conditions would suggest that there's going to be solar generation or excess wind energy on the grid, and actually it might be better to not charge the car that day, analyzing whatever's left in the battery, considering the journey that that person's got to do, and maybe it's better to charge that car in 2 or 3 days' time. Or maybe there's an element of the battery storage system that we can use to top up an element of the charge to make sure that that journey is comfortable without necessarily calling on the grid. And I think when we start to do that really kind of forecasted predictions of how the system should perform and validating whether what we predicted is correct, then we start to really tackle some of the climate challenges around maximizing the use of clean energy within the home. And that's what we're starting to do with our data sets. We're really starting to pull all that data in of the actual performance of these systems and running that training on the model to make sure that what we're predicting it can do and how it should perform, whether that was the right decision to make, and ultimately then making better decisions each time to improve the performance of the technology within the home. Where this goes next, and where we see the technology really starting to impact the infrastructure investments from network operators, is by bringing each of these connected homes into our virtual power plant, where we're starting to look at street by street simulations. So actually looking at those customers who are in the consideration part of the journey and what would be the impact on the infrastructure if they were to make the switch to heat pumps, battery storage, or EVs, but also looking at ways in which those homes that have made that switch and have got that technology installed can actually be used to support the grid And again, it's pure data. If we can see how the grid is performing in particular circumstances, and we know how those homes are going to perform based on the data that we're collecting, being able to send those signals down to the technology to either throttle back during periods where the grid is under pressure, or push energy to the grid in times at which the grid is in need. And we really start to build that kind of energy trading and the energy trading markets around that, to enable homeowners who maybe historically would have had a high capital cost to having the technology installed. We can now look at ways in which we can bring innovative funding solutions in, when we can validate that there is a revenue stream there through grid flexibility to actually underpin some of the capital cost for the installations. And that's one of the metrics that we're working under the energy as a service proposition that we're developing with ESC and with E.ON, is to monitor that the ancillary revenues that can be taken from the grid, the predictability of the performance in the homes, and can that be used to underwrite some of the financing and funding that's needed for these technologies to go in. So the power of AI to me is in three key parts. It's in that initial data modeling and simulation capabilities, taking learnings from installations that do progress to having technology in the home. It's then utilizing that data to maximize the energy management within the property and any vehicles associated to it, and then bringing those homes together in order to support the national grid in ways in which we can help balancing the energy consumption. Thank you very much, everyone, and hand over to some questions now.
Brilliant, Simon, thanks for that. There's already quite a few questions actually here, so I'll get started on those. John asks, I understood that when designing a heat pump system, you're required to assume certain target room temperatures, etc., rather than using the particular habits for the specific customer in order to qualify for the government grant. How do you get around that when taking a more data-driven approach?
Yeah, so when it comes to sizing the heat pump, absolutely right. Ensuring the heat pump is big enough, then when we do our calculations, we will simulate the heat transfer coefficient at those target temperatures. I think where we use the digital twin model is more to simulate performance, and I think that's probably one of the biggest challenges that homeowners have in this journey, is that actually getting comfortable that the predictions that we're making are actually based on how they use their home rather than an EPC, for instance.
Right. We've got one further up actually, which we think could be suitable for you here. So that from Peter, who'd asked, we've had tremendous success using physics-based models to do much, if not most, of the benefits of heat pump optimization, flow temperature control, and optimizing for weather forecasts and electricity price trade-offs. At home, consistently delivering a substantial running cost saving. Is it important whether or not the model is physics-based or a sort of black box AI?
I think it's both. We certainly started the journey with a physics-based model, and then the data and the machine learning aspect really starts to come in to prove whether that physics model, or to make the correction factors within the physics model. So where we found now is that actually the housing models that we have within the physics model have actually gone way beyond the number of homes that we'd even have in the UK, because each house model, each physics model, has to have variations when it comes to occupancy and climate data. So I think we start off with a physics model, and then essentially that is the model we start to train through the machine learning.
Brilliant, thanks. There's two here which are kind of related, and I was keen to ask about. Harvey's asking about, does us not rely on some consumers early on in the process receiving installations that are based off little data, potentially poor predictions? So customers early on will be essentially guinea pigs for the benefit of future customers. But I guess what I want to maybe expand on that briefly is that Bill talked about the the systemic blockers here, and one is about negative perception. So I'd also kind of like to augment that question with what your experience has been dealing with consumers as well, in terms of how they have responded to this. What's the sort of range of opinions? Because it seems to be that could be one that's tough to get around.
Yeah, 100%. I think fundamentally one of the biggest issues we've got at the moment, I mean, to answer the initial question, absolutely, customers are guinea pigs into the journey. But when you consider the customers that currently come into the process for are making performance related decisions based on EPCs, and those who are considering how the system's going to perform can quite easily look at the EPC performance data and decide that it's not relevant to how their home performs. So I think even with the EPC data, people are coming in as guinea pigs. What we're trying to do with our digital twin and simulation model is to provide greater visibility over how their home actually performs. And the general feedback we've had so far, it's a lot more engaging because people are becoming more aware of their smart meter usage, both energy and gas. There are free downloadable apps that you can get now where you can see that in the day, and people are starting to make decisions around that. And then what we look to do is to take that homeowner on a bit of a journey with it. So the logic when you apply solar and battery is obviously that your electricity consumption will drop. The minute you apply a heat pump to that, your energy profile changes dramatically. And that's what we try and convey to the customer in the first instance, is that their energy profile is going to change. And this is what we believe it's going to look like based on currently how much gas they consume for space and water heating. So it becomes a more engaging journey. And as we digitalize it further, we want to enable customers to kind of turn these things on and off and start to segment the load in the home. How much is being spent on heating, hot water, appliances, lighting, cooking, to be able to give that visibility, so they, when they do make those decisions to switch from, say, gas central heating to an electrical based central heating system, they can actually see the change in their profile. And then when they start to layer on things like battery storage and solar, it visually happens in front of them.
Great, thanks. Ben is kind of related to this then, really. Are you aware of research on consumer groups in terms of how much automation people want in their energy management? Do people not want to think about it or at all, or have some control? And I guess in general, I guess, is when you were approaching this project, were you thinking quite a bit about how, you engage consumers, and how to sort of broach these things?
Yeah, it's probably been outside of actually seeing the models and the algorithms come together. It's probably been one of the most interesting parts, and I'd go back to the Will Smith image that I put on. So that the if you talk to somebody about how we will monitor your home and we will make recommendations on energy improvements that you can make, you could pretty much take a 50-50 split between people that say, "Can't you just do it for me?" and the ones that say, "I really want to understand that before I go and apply it in my home." So it's been one of the elements that we've built into our model is, in terms of the software, is that you can either turn on or off the AI and the automation functions, or you can receive these recommendations and then go and decide to go and apply it to your technology manually, should you wish to. So it's some people are very concerned about it, giving away that level of control in the home. Some people, and I would say kind of the category of customers or category of consumers who are quite happy to hand that over, typically people that aren't that interested in their energy, want to save money but have very busy lives and just want somebody else to do it for them. So it is. I mean, the age demographic is a big split. Their level of interest and where they kind of fit on that adoption curve is a big factor. I think it will come in time as people build confidence with it, but it's definitely a challenge for the adoption.
Yeah, thanks.
And Simon, just on that, Sam, I know we're not meant to interrupt, but anyway, I think when we were in discovery phase for the DESNZ project, funded project recently, I think getting the catapult to our social science experts to actually talk to customers and ask the questions and actually feed back to you, I think that was really, really helpful for you, weren't it? Because I suppose you and I wouldn't necessarily ask the questions in the right manner. We'd probably be leading in the way that we asked them. And I think that's probably what we brought to the party, if that makes sense.
100%. The psychology behind these decisions is absolutely key. And as you say, the way in which you ask those questions is crucial, because unfortunately, in a commercially driven environment, you're probably going to ask questions in such a way that you kind of get the answer you want. Whereas the benefits of ESC being involved is you do get a real, true reflection of what the customers are thinking.
Brilliant, thanks. I'll just ask one more question, and then we'll move on to the next one. Steve's asked, so basically, and it's kind of another systemic blocker here, is about data, really. At the local grid level, in order to coordinate and optimize across multiple homes, data sharing would need to happen. How do you see this happening if multiple suppliers are involved? So, quite a
so just to maybe clarify, is this multiple suppliers from an energy retail perspective or from a network operator perspective?
I'm guessing this would be about linking sort of energy supply service operators within sort of a network management application.
Yeah, so I mean, certainly for us, where we sit as in the kind of in the energy data space, we can access smart meter data from any energy retailer with the consent of the consumer. So we're not necessarily receiving that data through the energy retailer, we receive it through Smart DCC. So that gives us the ability so that we're not restricted depending on who their energy retailer is, which enables us to kind of engage with a wide range of customers, but it also enables us to act independently if we see that a customer is on the wrong tariff for the way they run the system. We can make those recommendations.
Brilliant, thanks. So thank you very much, Simon. I know you can't stick around too long, but there's other questions if you have a chance to answer on there, that'd be great. But thanks again very much for that. And yeah, so I'm happy to move on to our final speaker, who is Lawrence Oshaks, the CEO of CityScience. He'll be covering the use of AI in buildings and district heat modeling. Lawrence will cover the role of district heating, zoning, and networks as anchors to whole city net zero strategies. So thanks very much, Lawrence, and please take it away.
Thanks, Stephen. Hi, I'm Lawrence Oakes-Ash, CEO of CityScience. So let me just see if my slides work. Perfect, they do. Just to give you a bit of background about what we're going to do, I'm going to give you a quick introduction to CityScience and our work. Then we're going to talk about heat decarbonisation, both the heat decarbonisation challenge and some of the heat network context and trends, which I think are really important. Then we're going to discuss whether to use AI, and I think there's a lot of chat, a lot of conversation in the chat around whether physics-based models are better or AI should be used, so we're going to actually cover that. And then I'm going to talk about what I think is the right role for AI in all of these systems, and then give you a range of different examples and case studies, some of which are ours and some of which are not. And then we're going to conclude and wrap up. So just in terms of CityScience, so we were established out of a single question, which is how do you take a city or a region to net zero? We predominantly work with local authorities and places, providing end-to-end support on net zero. That's from the evidence base all the way through to funding and delivery of the net zero actions. We cover energy, transport, carbon accounting, scope 3, and even things such as direct air capture. So we do a lot of different things across the space. Obviously, heat is a big challenge. It's 23% of UK emissions, and to achieve net zero, virtually all emissions from heat need to be eliminated. So when we talk about the scale of the challenge, the net zero challenge, then the challenge in heat exemplifies it. And if you've worked in this space, you'll realise that there's multiple behavioural, cultural and technical and financial challenges, one of which is just simply the upfront cost of doing the analysis required to make the right decision that other speakers have mentioned. Heat networks are likely to be a really big part of the solution. So the forecast is that it's possible that district heat will serve about 20% of the UK's heat. That's up from 3% of the UK's heat today. We were fortunate to have worked on a project in 2022 that looked about how we could reduce the upfront cost of heat network design. And that was through automating the process and then using generative AI. We worked with the University of Exeter. We worked with Professor Edward Keeble, who's actually a Turing Fellow, on the generative AI components of that. And when we did this, we think, as far as our knowledge, it was the first use of generative AI in infrastructure. It was funded as part of the Modernising Energy Data Applications Programme by BEIS and Ofgem. And I think what was important here is that the network itself, the network build and the network design had to have specific rules. So we did use a physics-based model and a rules-based model to enable how you would design those systems, and we'd automate it in such a way that you could run it multiple times. And that's where we used the generative AI techniques that we applied. Since that project, it's probably worth updating you some of the things that have changed. One of the key things that's changed is heat network zoning. So heat network zoning is due to come in 2025. This aims to be a further catalyst for district heat network deployment. So heat network zoning aims to mitigate some of the risks associated with heat networks to accelerate their delivery. So those risks include uncertainty. So zoning aims to reduce the uncertainty regarding both the process for designing a heat network and also ensuring that there's connection demand for that heat network. It aims to reduce the upfront costs by using a standardized methodology, and it aims to provide clarity on the roles and responsibilities at local and national levels around who's responsible for the district heat network design. One of the most important points from our perspective, having a district heat network, is that there's going to be a standard model, so a standardized approach. And we often see this with some of these critical pieces of infrastructure. Obviously, we've been talking a lot about buildings. Equally, in buildings, something like SAP is a standardized model. So one of the key things that we have to bear in mind when we're looking at AI applications in this space is the role of standardized models. So in heat network zoning, we're anticipating a standardized model, and we're currently working to try and make sure that our model reflects what's going to be in that as well. The other kind of key change, I think, more of a trend that we're seeing, is just the use of district heat networks as anchor projects for city scale delivery. So we're seeing, for example, since Bristol City LEAP, which is a big citywide decarbonisation fund, more and more local authorities are looking to use their heat network opportunities as a kind of an anchor pipeline for larger investment. So actually being able to combine that district heat with other types of projects to optimise funding and optimise how much of their local area energy plan pipeline they can get delivered. So I think one of the sort of big changes that we're sort of thinking about now is actually, whilst when we did that project we were optimizing the heat network itself, we're now thinking, well, what are these implications? We're obviously going to be thinking about optimizing the whole process at a city scale, which is going to involve a larger range of different projects as well. So just in terms of kind of what we did, and we talk about generative AI, I think it's probably worth defining what we mean. Certainly, since we used generative AI in 2022, ChatGPT has come in and been popularized. So the post-ChatGPT definition of generative AI, I think, has changed somewhat from what we originally intended. So generative AI, if you look on what people are saying it means today, is artificial intelligence capable of generating text, images, videos, and other data using generative models. So we didn't do that. That's not what we did. We were very much using a physical model to be able to create a design for a heat network, and then we would run that multiple times. And I know there's a lot of comments in chat about what's preferred, whether a physics-based model or an AI-based model is preferable. Certainly from our experience dealing with local authorities, one of the key things that we need is transparency and trust. You know, energy systems obey the known physical laws, and from my perspective, when we're looking at things that need to be transparent, then physics-based models actually do have multiple advantages over AI-based models. The key thing is that they're transparent and understandable. The second one is that they provide a solid basis of prediction based on those physical laws, independent of however much training data you have. So it enables us to generalize much faster than we would if we were relying on training data. And they're actually simple to code and integrate into wider computational processes. So I think from our perspective, when we talk about generative AI, what we really mean is about building a physical model and then running it continuously or repeatedly to be able to optimize a system using AI. So that's not to say that we shouldn't use AI, however, in any of these processes. So if you think about a kind of a pipeline for an energy model, it might look something like this. So you'll have some raw data, some sensors, maybe you'll have some background data that you get from national sources. You'll have a data store, maybe it will include some historic, some real-time data in that data store. Then you'll have some data processes. So maybe you're going to be infilling data or fusing data from different sources. And then you'll apply some kind of model. So that would be your energy models. This is really a context-specific mathematical model that's relevant to the questions that you've got in hand. You'll calibrate that model to various data sets as well. And then finally, you'll use that model for a specific purpose, really using it to support decisions. And that could be policymaker decisions, it could be homeowner decisions. It depends on the context. And then if you've got a digital twin here, then there'll be a feedback loop throughout all this process, making sure that the system itself is also improving. Now, I think one of the key learnings for us is that working in the policy domain and working on things like district heat, it's really important that there is a human in the loop in these sorts of systems. So we wouldn't use AI for the context-specific mathematical model. We think there are possibly and most likely to be better opportunities for that, but equally we're dealing in a world where there are standardized models that we also need to be aligned to, and we need to be clear that we're aligned to those models. But I think that there are four places, at least within a pipeline like this, where AI can play a role. So certainly capturing data, looking at using sensors or using drones or all those things, capturing data that we currently don't have in some of the other data sources that we've got available to us. That's number one. The second area where AI can be used is in either data infilling or in fusing data between different sources. So we'll talk about some examples of that as we kind of move through the slides. The third area is around how you calibrate models, in particular if those models are fairly complex and you want to calibrate them in a way that is as robust as possible. And then the final piece, and this is kind of where we were with that generative AI project, is how you use models and how you use AI in combination to support decision making. So the rest of this talk, I'm going to give you some examples of the sorts of things that I'm talking about there. So the first example is really around how you can improve data processes. So this is just at the data gathering stage, and this is an example of using images to predict whether solar panels exist, for example. Now, we talk about all of the sorts of features and all of the input data that you need for these domestic energy applications. Obviously, you might want to look at whether that home has solar panels. You might want to look at building geometries. You might want to get a sense as to the links between different building geometries that you currently don't get from something like an EPC record. You might want to look at how much space is available around that property for things like heat pumps and the deliverability of different measures associated with that building. So there's a whole range of things that you might want to look at using imageries or using drones. And there are a lot of places where you can go and kind of get this sort of data. So people like Absolar do this, DigiLab do this, and there's lots of open source options that you could use to try and capture data in the way that you want to look at inputs. The second application is really about infilling data gaps. Now, if we're thinking about things strategically, if we're thinking about a retrofit strategy, we want to have values for every single property. And if we look at things like EPC data or the needs data, those things don't have values for every single property. So we can use statistical or AI techniques to infill this data. And this is essentially what we did as part of the generative AI model build, because we needed to have heat demands for every property in a city, essentially, and we need those processes. So this is an example within our Cadence 360 software of our UPRN-based heat model. So it's every property we can kind of provide a heat number for. Now, I think it's also important to note that we invariably also want to validate these sorts of data as well. So if we're doing a strategic study, whether that's a local area energy plan, whether it's a local heat and energy efficiency strategy, which is what I'm showing here in this case, that data, those heat models also need to be validated locally. And often this is a kind of key part of that human in the loop process, especially if we're doing something that's going to be scrutinized by policymakers. We've got to make sure that data is validated. And often we're including local data sets as well that enhance that data and that prediction alongside the automated approaches. So I think that's a really important point here. And we use that in both when we're thinking strategically of analysis, but we also use it if we're looking at individual properties as well. So this is an example of a local heat and energy efficiency strategy we've done where we validated the data and the approach so that it can kind of stand up to scrutiny. But this is also a more localized example. So this is a we have an API for retrofit. It uses the same data, so that it means that any postcode in the UK you can get an initial result for. But then what we also do is we enable for every property, you can then make sure that the data is correct. So we give the best possible prediction, but it's got that human in the loop component there, so that whoever's looking at this can say, well, actually, I've got a different floor construction, or I've got a different boiler than the one you predict for me, so that we can get as accurate a version of the analysis as possible. And I think that this application also demonstrates one of the benefits, I think, of separating the AI from the physical model. So we are able to provide retrofit recommendations and outputs, but what we've been able to do this year for this model is integrate the open source home energy model, which was released this year by DESNZ. So the home energy model is essentially SAP 11. It's been released as an open source component, and because we've got this separation between the AI and the physics, we can then put in the new physics that's essentially going to be the official model for the UK, and then use this to make the retrofit recommendations. So, to our knowledge, this is the first retrofit recommendations engine that's actually using the home energy model, and I think that's something that gives it additional credibility. So I think that trust is an important component to remember whenever we're designing systems with AI in them. So then the next one I want to give you an example of is calibration. So obviously, if you've looked at SMETAs are doing this essentially at a building by building level using AI, often to calibrate a physical model. I wanted to show you one of a network. This is actually a transport network where it becomes very complicated to do this calibration. And so, here we've used various AI techniques to calibrate transport network models, and again working with the University of Exeter on the approaches to use here. But you could imagine this working for a district heat network or for an electrical network in the energy domain. And then the final example I wanted to show you is really, I think, what we see when we're talking about generative AI. The use of generative AI is really about how you use AI to optimize what are very complex trade-offs within energy decisions. So often energy system decision making involves multiple complex trade-offs. So it might be looking at what the carbon reductions are of a system, looking at the overall capital cost of the system. How does that cost translate into the cost to consumers? How many consumers do you connect from a different system, from a specific system design? How many consumers do you take out of fuel poverty from a specific design of a system? And so this is where the optimization methods can be really useful when they're combined with a transparent model. So the example here on the left was really our inspiration from this, which was an original piece of software designed by Cywalk Labs called Delve. And then on the next slide, this is just essentially where we got to with our generative design system for heat networks, where essentially we would be able to keep the human in the loop, but be able to provide the human assessors with a range of different design options, setting out what the different capital costs are, setting out what the different operational costs are, being able to show them the different sorts of networks that they could get along that kind of Pareto front. But overall, we're using AI in that optimization approach to try and make sure we're guiding users to what are some of the best decisions, but also recognizing that those policy trade-offs can only be really made by a human today as well. So just to bring it through to some conclusions, first of all, I'd say that AI and statistical processes can add value when integrated with traditional physics-based modelling workflows. Certainly for us, because we're dealing in the policy domain, that transparency and trust and use of physics models is a really important component. But an integrated approach, we think, provides the benefits of AI whilst promoting trust and transparency. Making sure that there are opportunities for local data to be added in, or human in the loop approach to ensure that that data is validated. We think that's also really essential, because a lot of the models that we're developing, go to some kind of scrutiny. And then we also think that model accuracy can be enhanced further by using AI at the calibration stage, especially if it's a more complex model. And then once you've kind of built a model that can be run again and again and again, or a design process that can be run again and again and again. This is where, using AI-based techniques around it, we can use those AI techniques to address some really complex multi-criteria policy or delivery challenges. And I think that's where we really want to sort of see the industry get to. So just some final remarks. How can we help at City Science? So we covered a few things today. We've got some strategic geospatial software, Cadence 360. If you scan the QR code here, you can log onto that, get some free energy data and start playing with that geospatial data. Retrofit recommendations, we can provide the software or we can provide an API. And again, that's based on a home energy model. And in services, we work on energy strategies and modelling, heat network feasibility, retrofit strategies, building monitoring, modelling and analysis, and retrofit coordination and one-stop shop services. So if you're looking to do any of those things, please email me. That is the end of my slides. So happy to take any questions.
That was brilliant, Lawrence. Yeah, thank you very much for that. Yeah, I've got a first quick question I'd like to learn a bit more about. There was actually some earlier questions when Bill was chatting, but I think they're relevant here. Is the potential computational cost of AI, and also how to scale up these things. Obviously, even with physics-based models, those themselves can be actually quite computationally expensive. So is that something you're worried about, or is it something that you think about with these models? And also the emissions they give up, I guess, is another question.
I think it depends on what sort of time frame you're looking at, because I think when you're looking at these sorts of systems, there's often two main time frames that people care about. One is the strategic time frame, where it's not a problem to have things that take a day or so to run. Obviously, then there's the real-time time frame, where invariably, if people are doing something on real time, that is much more challenging from a computational perspective, if it's going to be as computationally intensive. So that's where usually it will be a simplified model or an emulator that will be doing that if it's going to be done in real time.
Great, thank you. John asks, is there a danger of over-calibration? The graph shows a very tight fit. In my experience with calibrated models, if you use an automated system, there's a danger that you program in unrealistic assumptions that aren't helpful predicting the future.
Yeah, there's always a problem of overfitting. I think there's possibly more of a challenge in overfitting if you're basically just not using a physics-based model. So I would basically make the argument that if you're using an AI model in that bit, essentially you're training it on only the data that you see, whereas physics, has essentially been tested and scrutinized over many centuries. So it is naturally more easy to generalize it. But yeah, I mean, I think this is where you've got to be very careful with all of the sorts of AI that you're using to make sure that it's not just, fitting a curve and going to be overfitted.
Is the just to follow on from that, is there sort of interpretation, explainability? Is that something you've sort of built in? And the people you work with who are maybe not technical on this, how have you found that?
Yeah, I mean, explainability is a really important piece. I think probably the first project we did was to just use AI. This is probably now almost 8 or 9 years ago, and we were very, we assumed that people would be happy with a model that just predicted, but they wanted to understand much more detail about why. And I think that in this area of policy and public policy, being able to scrutinize models is a really important consideration.
Yeah, absolutely. Great. Sam asks, when talking about optimization, are you referring to traditional mathematical optimization algorithms as AI, or using a narrow definition of AI to cover things like
reinforcement learning? I mean, if we're speaking about the sorts of work that Professor Keedwell does at the University of Exeter, it's all nature-based algorithms, those sorts of algorithms, and often we're dealing with things that can't be optimized in the traditional way, so they're just too big to optimize without some sort of AI-based approach.
And I guess the final thing for me is, I guess, we showed those systemic blockers before. Are you, what have you found that has been kind of the biggest challenge in terms of implementing something like this in the real world?
Yeah, so, I mean, if we take the example of a property, then the cost, the upfront cost of doing the analysis is just really high. We're in the context of the, cost of living crisis and the actual money available for residents and citizens. So if you were kind of going to do a manual approach here, we've had quotes ranging for a whole house survey under like PASS 2035. We've had quotes that range from about £400 up to £4,000 to actually do a survey of a property and then make some recommendations. I think one of the challenges for more automated approaches, well, there's two challenges I think for more automated approaches. One is, even if you're using sensors, there's still a cost to sensors. So if you want to gather that additional data from the property, there's still going to be a cost to sensors. And obviously the higher quality of those sensors, the higher the cost. And so I think that will still be a barrier for, you know, homeowners to pay. Obviously, if you've got a smart meter, you can kind of get that data via the data communications company, but there's some challenges even then to kind of get established and then get a letter of authorization, so you can kind of get that. The other challenge, I think, is you might have an AI process that captures one thing, but there are so many things to capture on site that you might not. Yeah, so we've kind of got to the point where we don't think it's feasible to do it fully remotely yet, and would still make sure that there's some sort of site survey in the process. So yeah, getting those costs down is a real challenge.
Brilliant, thank you very much. So yeah, I think that brings us to sort of the end of the talk. So thanks again to all our speakers, Bill, Lawrence, and Simon. I think this has been really informative. We'll share this obviously on our YouTube later. It's been pointed out here that the chat has actually been really active here and interesting. So what we're going to try and do is pull out the interesting discussions there, as Sam puts in the chat, to kind of highlight some of the best things coming out of there. And so yeah. As I say, it's been brilliant. I just want to advertise that forum actually, which Sam put in the chat there as well. As part of advice, we're sort of developing this knowledge hub and forum, which we hope is going to become a useful way of people to interact and collaborate and share knowledge in there. And it's really going to depend on the community with the inputs that goes there. So what we developed is a few threads related to the discussion here, and Sam's putting those in the chat. They're going to talk about things like, you know, where some useful heating data sets are, organizations working in this area, and one inspired by today, actually, Sam just created about the sort of the intersection of machine learning and physics-based models. I think is a really interesting one. But you know, it's going to be completely dependent, hopefully, on the community sort of inputting into there. So I hope you do contribute, and I hope it can become a great hub for people to discuss things. So I just wanted to share that. There's another thing we have on Wednesday, which might interest the community here. We're going to be talking to Centre for Net Zero, who are going to be sharing a little bit about their Faraday tool, which is about generating synthetic smart meter data. So Sam's put the link in the chat for that. So yeah, and that's it really. I mean, it's been a really great day, lots of information out there, and it's been great to see sort of how AI is really being applied in sort of heating systems, you know, which is one of the greatest challenges, you know, facing our net zero ambitions really. So yeah, again, I want to thank Lawrence, Simon, and Bill, who've given some brilliant insights, and also, as I say, we'll be sharing this to everyone who registered, and it'll be in our YouTube. So, you know, if you have other further questions as well, please feel free to get in contact, and we'll do our best to answer. So again, thank you all.